everyone, thanks for joining, and we're going to wait just a moment while the audience logs in. Hello, this is Leah Freeberg from Fluke Reliability, and thank you for joining us today for this Best Practices webinar. You probably know Fluke as a test tools provider, and you may also know that we produce some of the industry's favorite reliability tools, from infrared cameras to vibration meters. But you may not know that many of the measurements our tools collect now flow automatically into EAM systems of record, and it happens via a framework that we call Fluke Connect. So our goal at Fluke Reliability is to better connect asset management data and teams with asset management systems to drive connected knowledge. And of course, that knowledge depends greatly on best practices in condition-based maintenance. So that's why this series of webinars explores reliability maintenance strategies, and that's why we feature speakers from a variety of expert backgrounds. Before the presentation, however, we have a few housekeeping items to go over. Today's session is being recorded, so your phone lines will be muted to minimize background noise. We will be answering questions both during the presentation and afterwards during Q&A. So take a minute now to find the questions tool in the GoToWebinar dashboard. Please feel welcome to submit questions as we go. We have 3 presenters today, all of whom have a variety of expert contributions to make. So you are welcome to ask questions during the moment as well as during the Q&A session. I will share as many of your questions as time allows for our presenters to answer. And if we have unanswered questions at the end, we will follow up with written answers. If you'd like to receive the slides from today's presentation, please let us know during the survey that appears at the end of today's session. So don't hang up until the survey appears and you've answered the questions, including the one about getting the slides. We're also happy to send you a certificate of attendance after today's webinar. You'll see a question on the survey about getting a certificate. Answer yes, and we'll send one to you. Lastly, a recording of this webinar will be available on the excelix.com website within a day or 2. And that's it for housekeeping. So now on to the main event. Today, we are very pleased to have with us 3 experts from Fluke Reliability, John Bernet, Greg Perry, and Dries Van Loon. And they'll be presenting on understanding condition-based maintenance tools that impact the PF curve. First, let's introduce John. As a mechanical application and product specialist with Fluke Reliability, John works with customers from all industries, successfully implementing their reliability programs. He has more than 30 years of experience in the maintenance and operation of commercial machinery and as a nuclear plant electrician in the U.S. Navy. He holds a Category II Vibration Analyst certification and is a Certified Maintenance Reliability Professional, CMRP. Welcome, John, and thank you for being with us today.
Thank you, Leah, and thanks everybody for attending, and look forward to talking with you today. Thank you.
Next, we have Dries Van Loon. Dries is a sales and project manager online condition monitoring for Fluke Reliability with 10 years of experience in predictive maintenance. He joined Proof Technique, which was acquired by Fluke in 2019 in Belgium as an application engineer in 2012 and moved to the company's US office in 2014 to set up a condition monitoring department. His department served all of the US on condition monitoring activities such as proactive maintenance, remote temporary monitoring, troubleshooting, and torque measurements. He became a certified ISO Cat 4 analyst in 2017. Welcome, Dries, and thank you for being with us today.
Absolutely, yes. Thank you for the introduction, and looking forward to the good discussion here today.
Excellent. And let me introduce Greg Perry. Greg is a senior capacity assurance consultant with Fluke Reliability. He has been a certified reliability leader with nearly 2 decades of experience in maintenance and operational best practices. Greg is dedicated to positive client relationships while bringing to the table a broad base of experiences in the areas of MRO and storerooms, world-class maintenance principles, world-class CMMS consultation and leadership, and in addition to delivering implementation and consultative services to clients, Greg also presents maintenance best practices sessions at leading industry conferences and has authored several online best practice webinars. Welcome, Greg. Thank you for being with us today.
Thank you for the introduction. Feel honored to be amongst the peership that we have today.
Right? It's going to be excellent. And for those of you who are used to our usual webinar format, you'll notice a few things different already. Today's session is part presentation and part panel discussion. And since we have 4 of us, that's why our webcams are on. You are welcome to use your full screen mode if you would like, but know that when we do a poll question, you will need to minimize your screen back so that you can answer the poll questions. So to start things off, we're going to run a poll real quick. And then Greg is going to walk through some background and coaching on the PF curve. And then Dries and John are going to go a little deeper into the measurement methods called out by the PF curve, so we can get at that ultimate question of what asset health data should you collect. And again, I want to encourage everyone to ask questions as we go. But to start, I am going to allow you all to answer this first question. What level of condition-based maintenance have you adopted in your current job plans? And so think about the assets that you are applying some degree of condition-based maintenance against, and think about what percentage of that is condition-based versus a different maintenance strategy. So is it more than 35% of your assets are receiving condition-based maintenance? Is it 25 to 30%? Is it 15 to 25%? Is it 0 to 15%? Or not sure? And not sure is completely fine. If you're only doing a little bit of condition-based maintenance, that's fine as well. So take your best guess. There's no harm in an approximation here. And the idea, of course, is to give our presenters an idea of what the audience is doing at this point. So to share our results right now, we have 24% who are doing more than 35% of condition-based maintenance. We have 18% at the next level down, 15% doing 15 to 25%, and 35% doing 0 to 15, and 9% not sure. Panelists, what do you think about those results?
Looks like there's a good, healthy areas of opportunity here with 35%, with 0 to 15% of adoption. But then there's also on the other realm, the other side of the coin, there's already a good, healthy level of participation. So it sounds like both sides of the coin are going to benefit from today's webinar and understanding what opportunities you have to start bringing in condition-based maintenance and adopting them into your current job plan. So it's a good spread.
I had similar thoughts.
Yeah, if I could add one.
Go ahead, John.
Oh, what I was going to also kind of throw up a disclaimer is that, you know, keep in mind that when you look at best practices, not all machines are going to be on a condition-based maintenance. So that's the reason why we don't have 100% up here, is because even in the world-class or best class, you know, companies in the world, you're never going to be at 100% because it's a mix in your plant of reactive and calendar-based and condition-based. So that's why these numbers really look pretty much like what the industry is seeing right now, because not everything is going to be condition-based. But that's what we're going to talk about today, is which machines should be condition-based and which machines don't need to be.
Exactly.
Go ahead, sorry, I interrupted.
No, that was a perfect interjection, because we want to encourage everyone today to ask questions. This is a question-driven presentation, and we want to hear from people at all levels here. And again, there's a reason why it stops at 35% there. All right. With that, I am going to turn the mic over to Greg to do some introductory explanation of the PDF curve. Greg.
Absolutely. Thank you, Leah. So PF curve, pretty sure most of the attendees here should be familiar with the PF curve. And if you're not, I'm going to give you just a little brief overview, just a little bit. I'm not going to go into big detail, deep dive into PF curve. But 1978, Nolan and Heap, back when they did their reliability center maintenance study, they put into a depiction of how do components fail, okay, and over time. So what you're looking at is original Stanley Nolan and Howard Heap's PF curve, and what we want to point out here is just the basics. And if you notice, I put the check engine light sign right there on a potential failure, but you can actually move that check engine light sign. Everybody's kind of familiar with the car and they have an early warning, right? And that check engine can actually be moved all the way up to point A. It can be at point A, it can be at point B, okay? But I put it at point C just for this discussion. And then as you see that the component is in the act of failing, all right, over time, it finally reaches what's called point D as a functional failure, okay? And so when we have functional failure, what we mean by that is that, and I think next slide, Leah, I think we go into a little bit more definition of that. Okay, so when you actually get the functional failure, we're talking about the inability for an item or the equipment containing it to meet a specific performance standard. Okay, that's not total failure. So I had a little fun with putting a little screenshot of some firemen down here trying to put out the car. So we had a little indication earlier on, right? And then all of a sudden, boom, it's on fire. So once you've gotten below functional failure, you've now entered into the zone or the twilight zone of total failure, okay? And so we don't want to be there. That's not where we want to operate on. You know, truly, we want to try to catch failures on the PF curve happening, or degraded failures happening sooner rather than later, okay? And so just a little bit of history there with the PF curve. It's a great tool. We use it in reliability maintenance quite often, and I consider it kind of the Bible, if you will, and part of the dogma of how we go about trying to apply the right strategies to eliminate, mitigate, and to directly target failure modes of our assets, and namely the components. Next slide. And so back in 2006, I believe, well-known author Doug Plucknick is also the creator of RCM Blitz, introduced to the world what he's called the expanding the curve. And I don't know, you probably have seen his iteration of it. It's called the DIPF curve. So what I've done is just simply try to explain that in our own way, where you actually have the right side, which is called the PF curve, classic PF curve, if you want to call it that. And then on the left side, Doug introduced what we call the proactive side of the PF curve, okay? And within the proactive side, it starts with designing for reliability, commissioning for reliability, install for reliability, and kind of a new entry into this concept of supply for reliability as well. Okay, very important. And then you get into the precision maintenance techniques that you can apply and adopt and deploy, and then you can get into the proactive maintenance techniques that you can apply and adopt and get into. And everything here is left of the PF that we're talking about. So we gave it a name, or I gave it a name, or actually we all gave it a name. It's not me, it's we. Inherent reliability. How many people here have heard recently what inherent reliability means? Is anybody familiar with it? Is this your first time hearing about it and learning about it? But inherent reliability basically states that you have to first build it design fit for purpose, okay? And then you have to set about the tools and techniques that you can use to maintain that higher condition for which it was designed to deliver. So inherent reliability, if we think about it, if we didn't design it for reliability, we didn't commission it for reliability, we didn't install it, we didn't supply for it, then we're actually impacting the classical side of the PF curve called inherent availability. Okay, and inherent availability, the entire realm is all corrective maintenance. And I think that was part of the revolution. That was a revelation that people had to come to realize that, wow, so everything we're doing on the PF is corrective. So we call that, especially the PF interval, right, you see there is the corrective domain. Next slide, please. Okay, so I'm not going to read this to you. The slide deck will be available to you, but basically what I just talked about with inherent reliability, we call that the maximum attainability of the system, the asset, the components. Okay, and so really all we're trying to do is make sure that we are designing the asset and the component so that it has maximum reliability. All right, in which we also call it attainability. So inherent reliability is all about that concept. Next slide. So then how does that impact the PF curve? Well, it impacts it from maximum maintainability. So if it didn't have total inherent reliability, okay, then you're left with a certain amount of maintainability with the component and the asset. And so the important takeaway here is, and I can tell you and I'll promise you, no amount of maintenance that you can do within the inherent availability realm is going to increase the inherent reliability. Okay, and so just kind of give you some basics with the PF curve, what we call the classic PF curve, and then what we call left of the PF curve, which is inherent reliability. What do we mean by that when we speak inherent reliability versus inherent availability? Very, very simple, broken down. But one of the things I wanted to also note was the PF interval. So the inherent availability is the steady state availability when considering the corrective maintenance downtime of the system. So this was actually back and defined in 1996 with Weibel. So trying to make sure that we understand what we're talking about with corrective domains, okay? And then more importantly, and next slide, what we want to do is we want to understand what are the right, what we call modalities or the tasks really to apply on the classic PF curve within the inherent availability realm. Okay, so everybody's familiar with these classic modes here, fault direct modes. So that's your inspection based techniques or incidental based techniques. Incidental based techniques are going to be your fault finding. It's going to be your these are those work requests that are coming in. All right, this is where we found a problem. It's either before functional failure or after functional failure, or we actually are deploying just an inspection-based technique to go out there and just inspect and see if we can find things from a visual. We're talking human inspection piece here, okay? And then we get into the time-directed mode. That's your classic PMs. That's your classic preventive maintenance. Okay, these are your time-directed, calendar-based or meter-based interval type scheduled preventive actions that you actually are deploying against the failure modes. Okay, and so we move left with condition, which are condition-based techniques. And what we're going to be talking about when I'm done talking is within this mode, the condition-directed mode, condition-based techniques, and how to properly place this within your job plans and opportunities to use these particular types of tools and techniques that are also called predictive maintenance. And then you move to the left is data-directed mode. These are analytic-based techniques, and that's where we're at with right now in the IIoT of things, especially on the bleeding edge of it, to where we are starting to apply empirical data that we're gathering from the condition-directed modes, and we're trying to actually learn more about being more, I guess, prescriptive. And I hate to say that word because that's not really what I want to talk about. But yes, we want to use and get more towards data directed. Okay, so how can we get there as well? Now, here's the revelation. Again, remember I told you everything you're doing on the PF curve, especially with the PF interval, is a corrective domain. So therefore, all of these tools, all the techniques, and all of the tasks and all the modes that you're doing here live square in inherent availability. And all of you're doing is driving failure, eliminating, mitigating corrective activities through either discard or restoration. Okay, so when you go out and you do your FMECAs and you're doing the FMEAs and you're doing your reverse RCAs and you're doing all of the wonderful reliability-based and reliability center-based maintenance practices, all right, you're trying to align one of these types of modes to the failure mode. And so as John mentioned earlier, when spot on, you got to realize that you're going to be doing a lot of these different types of modes within your own job plan. Okay, so the fault directed mode might be the most efficient strategy to follow. Time directed might be the most efficient. Condition directed may be the most efficient. And then, of course, if you can do data directed, great. That's where you really want to get to. But you've got to remember, all of these are corrective activities within the inherent availability realm of the PF curve. Next slide. So really moving towards being asset health centric is really the underlying premise of condition based. Okay, so that's really where we want to try to move on our journey, correct? And as John pointed out, you're not going to do 100% of condition based. Okay, that's not realistic, and that's not what we're promoting at all. What we're wanting to make sure that you get out of this webinar is understand that there are opportunities out there to use tools and techniques, okay, what we call predictive maintenance tools and techniques, that actually help you with being condition based, where it's most appropriate, where it actually returns the better value. And as I heard earlier as well, we talk about best practices. Well, best practices really are what you practice best that returns value back to you and your organization. And so moving towards an asset health centric, condition based is going to be best practice. And I'm hoping that you learn more from this webinar so that you can become more astute at practicing it best yourself. Next slide. So I just want to kind of reiterate here with matching failure modes to measurement methods on the PF curve. You just remember, you're going to be doing a splattering of fault directed, time directed, condition directed, and hopefully some data directed, all within how you're addressing these failure modes of the components. Okay, and what are you applying best so that you can find the component in the act of failing sooner rather than later? That's the whole idea with the PF interval. Because if I can find it at the potential failure point, which can be further left, all the way to the left of the condition, depends on what strategy, it depends on which tool, it depends on what technique you're using. But as soon as I can find it at a potential failure and then go in and act on it, okay, then I should be able to keep the asset in operating context 100% and maintain its asset health. And of course, remember, if you took a ding on the inherent reliability side, then there's no amount of maintenance you want to do to raise the inherent availability. Okay, you're only in a maintainability mode is what you're in.
So we already have a question, Greg.
Sure.
And it's probably one that you anticipated. So someone says, so you're calling PDM corrective and not predictive maintenance?
Correct. Yes. Predictive maintenance doesn't predict anything. Okay. Predictive maintenance is tool or technique that you're using. Okay. So that you're using ultrasensory technology to actually try to identify potential failure. I'm not predicting the potential failure using predictive maintenance. Okay. And I can't predict the functional failure mark either using predictive maintenance. But I can use this as a tool and technique to go in there and try to find the asset or the component in the act of failing a lot sooner on the PF curve than using any fault directed or time directed mode. Okay, so no, predictive maintenance doesn't predict anything. It's a tool and a technique that's found up underneath the strategy of condition-based maintenance.
Okay, I think what the questioner is getting at is the definition of reliability. So what analysis do you do to achieve reliability?
Well, reliability, if we go back to the PF curve as this whole entirety, that is reliability. So what are you doing in inherent reliability realm? And then what are you doing in the inherent availability realm? Okay. And so reliability isn't just to the left of the PF curve. No, but it does encompass everything from designed for reliability, commissioned, install, supply, and then of course, what type of precision maintenance techniques are you adopting and actually using within your culture? and your proactive maintenance techniques that you're actually adopting and using within your culture. So if we think about the definition of reliability, I always think synonymously with culture. How reliable or what's your culture? Is your culture where we just want to not really care about inherent reliability and we don't care about inherent availability? We just want to make sure that we just go fix things? No, reliability starts all the way from the sweeper to the CEO in your organization.
Indeed. So audience, you are submitting some excellent questions, and I'm going to relay one that's for the entire panel, but more specifically for Dries and John, as you are moving on to talk about different inspection techniques, because someone is asking us to differentiate between condition monitoring and predictive maintenance, right? So for example, vibration monitoring being a condition monitoring technique and how it predicts anomalies, right? And then we perform the predictive maintenance on it. So think about that condition monitoring versus the other terms that we're using here as you go through the various inspection modes. I'm going to move forward, audience, to the next section, but I'm going to continue to interrupt with your questions, so keep typing them in, okay? So Dries, on to you.
Yes, perfect. And I think Greg did a great job there in kind of placing where we are now, right? I always try to start every meeting with make sure everybody's looking at the same picture and we speak the same terminology. And even just in such a good introduction, you see there's already some conflict, right? And I think where it also comes from, to add a little bit to what Greg was saying, is that some of these condition-based technologies, which for example, vibration I'll be talking about, are also used on the proactive side of things, right? Because they can help us to make things better. Right? So we use that same vibration technique to learn certain things that we can use on the proactive side. Like, hey, now we learned something on the PF side of things, and we go back and say, hey, let's make it a little bit better, maybe proactive about it. And then we typically use the same tools or input from the same tools for that. So that's where I think a lot of sometimes the confusion comes from, that there is some overlap between the different PF side and then the before the actual failure mode starts, right? Okay, so I think that's a good add-on. It was indeed a great question there as well. If we look at when we're on the PF side and how we're gonna find these different failure modes, you see that on the PF curve, there's different technologies, and depending which, I would say, almost vendor or which enthusiast of maintenance you ask, you'll see that they put the different techniques in a different order, but that's also truly dependent on the failure mode you're trying to detect, right? We'll talk today about 4 or 5 different techniques to match, find these failure modes. And depending on the failure mode, which techniques work best. And I say techniques on purpose, not because I have a weird accent, but because it's a multiple of techniques that will give you the full picture, right? It's not that there's one holy grail, because else our presentation today would be very short. But it's always a combination of different of the technologies that will give you the full picture and give you, let's say, the true insight and the actions that you can take from that. So we're going to zoom in on each of these different technologies and kind of say, hey, these fit good with these type of failure modes, and to give you a little bit of a better idea where does what fit. And then one last thing on this slide also is the data-driven side. That's kind of new with this IoT world now, and trying to connect everything into this ginormous databases and trying to learn, use computer algorithms to learn lessons out of the data for us, right? Instead of doing everything with a trained analyst. So those, of course, you need to have the data first, right? So you need to have some kind of condition-based technology in place that can feed into your data-directed system. So those definitely are hand in hand and are definitely developing really quickly now with sensor technology developing, as well as the AI side or the automated side of that as well. So if we go dive into one of these technologies, we'll start with vibration, mainly most commonly known or most commonly used on typical rotating equipment. And a first point here is that it's a good technique to not only monitor the condition of a piece of equipment, but also then define, hey, now I have an issue or I have a red flag in my data. Okay, I can also use that same data to find the root cause of that failure. If we look at a very simple piece of machinery, and probably all of us have multiple of these under our supervision, right? A pump right there on the right-hand side. I mean, we can find anything with vibration with the right setups from machinery failures, from typical imbalance, misalignment, looseness, which already cause probably 70% of all machine failures on typical rotating equipment. And then additionally, we can look at bearing failures together with lubrication issues, and from a very early stage on. So that's kind of helpful that we get a very early warning, a very high up on that PF curve. We can get our first indications of a bearing issue, and additionally, we'll also be able to pick up certain electrical issues with typical motors or VFD-driven machines, and then of course, process-related vibration as well, right? If there's flow or other types of issues there. So you see on a fairly simple piece of equipment, let's call it a motor direct-driven pump combination here, most of the failure modes were able to pick up with vibration, and not only, hey, throw a flag saying, hey, something changed, but also then after that, go into the more detailed data to say, hey, what is causing my change? So you can actually prescribe a corrective action out of it, right? Because that's really the goal, to out of the data to then say, hey, this is the action that we should be able to take. And sometimes action is, yes, let's investigate deeper, but 90% of the time you're able to come up with a maintenance action to improve the situation. And so on a simple piece of equipment, you're able to detect probably over 90% of the different failure modes using this vibration technique if it's properly implemented and used. So that's also why it's very commonly used, right? Maybe it's one of the more complex technologies to master. That's why there's a couple of vibration levels in vibration to reach. And to get more in depth in it, but that's also because it gives us most information, right? Most in-depth information. So if we go to the next slide, we kind of divide that up as well when we talk about looking at the different measurement methods, right? A vibration analyzer, if you ask two people, they'll probably tell you two different things what it actually means, right? And we can go from I'll start on the bottom of the screen here. We can go from very basic systems for more the screening, right? Saying, hey, throwing that flag, hey, there was a change in the vibration levels. As some basic wireless sensors, they're very commonly available today, as our 3561 is, or very basic vibration handheld devices like an operator vibration pen or something, and with minimal experience, minimal training, people are able to use these tools and already start monitoring for changes, right? That's really what you're trying to do, like detect a change. And then if we take it one step up on the diagnostic side of things, to say, hey, we have maybe some more advanced wireless systems or a more advanced handheld analyzer that can not only collect the data and find a change in that trend data, that level 1 data, but also then have some of the back-end data, the more advanced data, so we can draw some root cause analysis out of it, and we can draw some usable conclusions out of it. And we call that, like, say, a level 2 worth of training, which kind of matches the ISO certifications for vibration as well. And of course, you need some experience to be able to successfully use this technology. And then on the top of it, we look at a true analysis system, typically a continuous online monitoring system that will continuously monitor the equipment, and that's really for your top players in your plant, right? The 10% of the very most critical assets, where you say, hey, if something goes wrong with this piece of equipment, we'll really the plant is down, right? It's going to cost us X amount of dollars downtime. So those are the ones that you want to be on top of, and that's where you would say, hey, we really need a true in-depth and continuous monitoring system on there, and that would be in that analysis category. If you look on the right side here, we kind of use those same colors to define also, hey, which assets should I use, which type of technology, right? Which method? We have the screening tool, which basically could use for every piece of equipment you have in the plant. I mean, an operator rounds, they look at all the equipment anyhow, because everything has a certain function in the plant. So they use everything. Going to diagnostics, say, okay, maybe we exclude some of the very low-hanging equipment that's not very has no influences, it breaks down to our process. So we say, okay, with those we can maybe come around with a periodic measurements, going there every month, every 2 months to collect the data, and then we end up in our top tier with the systems that, hey, if those break down, we'll really have downtime on the plant. So those should be really you should have data automatically and readily available to make sure that it's being monitored correctly. And in the past, I think one thing I want to add on this slide is in the past that we would have vibration meters, very basic tools, and yes, an operator would take a piece of data and, okay, let's write it down on an Excel sheet, and then that data disappeared into nowhere, right? And that's really a big advantage now with this IoT world we're living in, is that even data from very basic tools to the data from our most advanced tools can all be used and can all be synced into databases, visualized in certain dashboards, and that's really how a lot of value is added, right? So that's why any of these tools really adds value to the decision-making process at the end of the day. Okay, and then yeah, let's jump to the next technology here. I think we want to talk about is lubrication
Can I ask
and
you a quick
oil.
question before you move over to oil? So I have a lot of questions coming in that are similar, and a lot of it has to do with that data aspect that you were just talking about, and at what point it becomes analytics. And so you are advocating that all of these can be converted, can be used to collect data. Is that correct?
Yeah, and then I guess the question is where am I in a purely condition-based system versus, hey, where does it become data-driven? And it's exactly. Really, let's say, a fine line. And I would say as soon as you use some of this screening data, for example, from a very basic, let's say, vibration pen, and that data, with, for example, Fluke Connect, can end up in your eMain CMMS system, right? So it's able to be used as a very simple machine status on an asset level in your CMMS system. So as soon as you kind of automate some of this, saying, hey, I got some data being collected, can be manually, can be with a device, can be continuously with an online system, and you feed that back directly into, let's say, a visualization platform of some kind, as well as then, hey, link it to on an asset level in your CMMS system. I mean, then you're already making data-driven decisions, right? Because then you can say, hey, as soon as I have a warning on that level, I can trigger a work order, for example, for a technician to go inspect this asset to collect more data, right?
Right.
So that's the most basic way of already using some data-driven, some automatic warning. And I see Greg moving his head in the right direction, so I'm happy.
We have another person who just wants to confirm, Dries, that when you talk about applying these measurements, you are talking about the component level as well as the equipment as well as the system level, right? So it just depends on where the criticality has been defined.
Yeah, correctly. I mean, at the end of the day, it's always a component that starts the failure, right? And that will result in the end of the day, your whole system being down. So you monitor technically on a component level, but that will influence then the status of the whole asset and as well as the system at the end of the day. And then maybe one thing I want to add on that previous question is on when we talk about analytics at the most basic form I explained, but today we're also already using advanced online monitoring systems and automatically having AI engines and other types of machine learning systems continuously looking at that data, and they could pinpoint failure modes, right out of the data, right in front of you, and like, hey, ping, here's a flag, and it's not a flag, a condition change. No, it's a flag saying this machine has an imbalance. This machine shows an early bearing damage. And so we're already going that far with this
Yep.
AI and this machine learning technology, and it really. Because a computer, if you think about it, it's not very good at doing a webinar. If your internet is not good, but a computer is very good at looking at a lot of data really quickly, right? And they can kind of crunch that data for us and go through every second piece of data on a lot of equipment, and kind of flag for us like, hey, this is one that jumps out, and this is one that needs attention.
Thank you.
That's okay.
All right, back to you.
Okay, and then we talked about vibration quite extensively because it's obviously very commonly used and a great technology on a lot of types of rotating equipment specifically. Oil analysis, another technique that's very widely used, as specifically on bigger rotating equipment or even hydraulic systems, right? In the rotating equipment, we think about gearboxes, any type of sleeve bearing application, as well as like reciprocating engines and compressors, which are coincidentally maybe also the equipment that we find on our most critical equipment out in the plant, right? And so those are the ones that can really benefit from oil analysis. And again, it's a condition monitoring tool. So hey, it can help us to detect a change, but it's also a root cause analysis technique, because out of that oil data, we can find, hey, it's the type of oil, the type of wear that was detected can be analyzed. Say, okay, this is from a bearing, or it's from a gear, or it's some component of your hydraulic system, right? So it can help you find the root cause of the failure as well, which I think is very important when we try to implement the technology to monitor a piece of equipment. Monitoring it is one thing, but what are you going to do when that red flag shows up, right? Are you going to, now what? Oh, we have a potential failure on this piece of equipment. Now, do we need to call in an outside consultant to come and troubleshoot this piece of equipment, or do we have the proper data to make that decision then and there? And that's an important thing to keep in mind on all these types of technologies. So oil analysis, very useful on big rotating equipment, which is typically also our most critical equipment, gearboxes, sleeve bearings, reciprocating engines and compressors, as well as large hydraulic systems, which are pretty common as well. And then if we look at the next slide, we'll see that that it kind
We lost Dries.
Dries, I think your audio may have cut out. If you can hear me.
Hey, sorry, I'm back.
Thank you. So we lost you at the beginning of this slide. I apologize.
Okay, not too bad. No, that's my bad. And from a screening, we do with all these technologies, we do the same thing. We say, hey, we divide it in different categories, right? We can do screening and diagnostic, or we can go really in depth and analyze that failure to make sure we can draw conclusions out of it. And from a screening perspective, simply like an oil glass, looking at the oil, making sure it looks clear, there's no foam. And to monitor an oil temperature, are very basic things that can be done, but can already tell us a lot about the condition of that asset. Diagnostic, as maybe some basic oil sensors for humidity, for general wear condition, or basic lab analysis, right? Taking samples every month, every 3 months, send them to the lab, and they will tell you, hey, this oil is healthy, there's no wear particularly in there, and so on and so forth. To then more advanced analysis, where we maybe install a continuous system to do this wear analysis and count particles. Hey, which size of particle is passing through this oil sensor? How many of them? So you can actually see the wear increasing, and you can define if it's ferrous, non-ferrous, from which components it would potentially be causing, right? Or then really in-depth lab analysis, where they would take the oil, take, for example, the wear out of the oil and under a microscope tell you like, hey, what type of metallurgic failure potentially caused that. So they can go very in depth on these types of on oil analysis as well. And so with the same idea of the different levels depending on your asset criticality and what you're trying to define, you can define what is the best, how deep should I look into this technology, or how far should I implement it to make sure that I catch those failure modes as they come on. Okay, I think that's what I had here on this slide.
Okay. We have some questions about oil as well, and I'm going to ask you to answer just briefly. So it sounds like some people are still evaluating how predictive oil analysis can be, but other people are questioning about whether we're at the point where we can do censoring for oil. Is that something that you would want to answer, Dries?
I mean, I think oil is, again, it adds value to the bigger picture, right? With only vibration, with only all these technologies by themselves will not give you the full picture. So oil is definitely a critical component of that bigger picture, and it has proven its value, I think, over and over. And then when we talk about sensors, it's, again, you can implement any level of sensors. That technology is there, and the results have been shown, I think, for those specific assets where the oil is a critical component, that they definitely add value in that bigger picture, yes.
Right. And then if you are using oil analysis, and this is, I understand this is a larger question, but how do you determine the relative frequency for running the diagnostics?
I think this question can be asked about any technology, right? When do we say we're going to do it? When would you say we're going to do it quarterly versus doing it bi-weekly or continuously? And it really depends on the failure mode you're trying to detect, right? And a lot of times, historical information on that type of failure mode, maybe on a similar piece of equipment or from the OEM, is important. Say, hey, how quickly would something develop into an actual potential failure point, right? Or an actual failure. So then you know how much time you have to detect it, and that's really defining how often you should do use a certain technology.
That's really core to this whole conversation, isn't it?
Yeah, exactly. It's really that everything is around that failure mode, right? And then that will define the technology to use, and then about which technology implementing, and also how frequently you take the data and absorb it.
Exactly. Thanks, Dries. I appreciate it very much. John, do you want to pick up at this point? Okay, now I'm not.
Thanks.
Oh, there we go. Okay.
Quickly, let me say thanks to Leah, and also to Greg and to Dries for their great overview. I have the hard position of now following these two, but anyway, let me. So I'm really going to kind of wrap up what Dries has started, and also what Greg has started, and so this slide is really to show exactly what Dries has been leading up to, and that is we don't want to just pick one technology and walk around our plant and say, I'm doing condition-based maintenance, because it takes more than one technology, because it depends on your problems. The biggest problem we've seen in customers starting up, what technology, is they try to use one tool. What's the old saying? If you only have a hammer, everything looks like a nail. Well, that's a problem. And so what we really want to do before we start figuring out what we're gonna, what technology we're gonna start with or we're gonna pick, is we need to look at our expected failure modes. And so without getting too deep into that, let me just kind of quickly go over that, because if you think about it, think about your asset, and we're going to be measuring the individual components like Dries had said, but that entire asset, from electricity in to work out, anywhere along the line, it could go down and you're going to stop making Cheerios or whatever you're doing, okay? So Dries has already introduced the vibration, which in most cases, a lot of people think that's the biggest bang for your bucks. But again, that's kind of at the, not really a tail end, but that's really the work end of this asset. Dries also covered oil analysis, because there are some oil-cooled machines that need to be monitored. So we can't just do vibration on a machine, and we can't just do oil analysis on a machine. We need to figure out beforehand what are our failure modes, because that should dictate what we're going to be using. All right, next slide. So let me quickly wrap this up. And so motor testing. Remember, we looked at 5 different technologies, and one of them was motor testing. So we can think about the vibration as telling us what's going on inside the rotating components of the machine. But what about the electrical components? Remember, we showed you that there's a lot of electrical components before we get to the motor. So motor testing is going to allow us to look at the motor and find out a bunch of things about the motor health. And so there's 2 different types of tests, energized and de-energized. And here I've shown you some of the tests. I'm not going to get too deep into it, but let's move on to the next slide. All right, and on the next slide is thermography. Again, we don't want to just use one, because just like oil analysis and ultrasound I'm going to talk about next, thermography is also an important tool. So what is thermography going to allow us to do? So next, please, Leah. There are a couple of different things that thermography is going to help us do. Electrical, it's a great tool to look for faulty components in the electrical, the fuses. It's a great support of mechanical as well, because a picture is worth 1,000 words. Here we can see a mechanical problem, a machine that's misaligned on the right, and you can see that what it's supposed to look like is on the left. And then along the bottom, you see other mechanical things like a belt and a steam trap, and also process parameters, tanks, and that kind of stuff. So sometimes seeing is believing, and sometimes when you say you've got a high vibration peak, the boss may not believe you, but if you show them a picture, now they believe you. So that's why we need to use different things. All right, next slide. And we'll kind of wrap this thing up. So our next slide is going to be ultrasound. I like talking about ultrasound because Dries has already talked about this. One of the biggest problems that we have is when you ask a customer what's one of their big problems, they're going to say our air compressors keep breaking down, and we're continuously having to chase air compressors. We're spending all of this time fixing air compressors. And at our own facility at Fluke, we have the same problem with air compressors. Well, guess what we found out? It wasn't the air compressors, it was air leaks. So instead of fixing air compressors or keep adding air compressors, if we fix the air leaks, we can actually turn off some of our air compressors. So that's what you want to be looking at. And so ultrasound is a great tool to help us find these air leaks. Again, a picture's worth 1,000 words. So we can use ultrasound to look for air leaks. We can use it to look for valve actuator problems, steam trap problems, lubrication problems, electrical safety, tank tightness. So look at your expected failure modes. Okay, let's go to one last slide and we'll finish this up because we're just about out of time. And in this last slide, we're going to put it all together. So what is our summary? The summary is match the right tool to the right technology. Don't just have a thermal camera and walk on your plant and say, hey, I'm doing predictive maintenance. Well, guess what? You're only doing part of it, And so this is a good slide that shows there are different technologies. There's ultrasound, there's thermography, there's oil analysis, there's vibration. Do an expected failure mode analysis of your plant. Find out what things are causing you the biggest problems. What's keeping your team up at night? That's what you want to go after, and that's going to help you determine what tool and what technology. The real answer is you're probably going to need all of them, but let's see where you're going to start at. Okay, I'm done, I think. Next slide.
That was impressive, John.
Okay, thanks.
So, audience, I'm going to ask you which tools you're using because that will help us during the Q&A, and we may run a bit longer just because we have so many questions and we want to be able to get to some of them. So Audience, if you'll tell us now which techniques you're using, then that'll help our panelists as they formulate their answers here. So and feel free to choose as many as you are using, because as we have just heard, you don't use just one technique, you use them in combination, and you use them depending on the failure modes and the criticality and the overall operating conditions of the equipment. So let us know which of these you're using. I'd love to get at least half the audience contributing, and it looks like we're just about there. So I'm going to give it 5 more seconds, and then we're going to share the results with everyone. Excellent work. Thank you, everyone. Again, choose as many as apply to you. Okay, and 1 more second, and I'm going to close this down, I promise. Okay, I'm closing it now, and I'm going to share the results with everyone. So we have a lot of vibration monitoring happening. We have a lot of thermography and a good amount of oil analysis, followed by electrical testing and ultrasound. Well done, audience. All right, so at this point, what I'd like to do, I'm going to hover on this slide for a little bit, and audience, you are welcome to write down the email addresses of our panelists. In case you want to email them directly afterward, you are more than welcome to. Again, at the end of this session today, you will receive a survey, and if you answer that you do want a copy of the slides, we will send a copy of the slides to you, including these email addresses. But after a moment here, I'm going to flip back to that PF curve and the failure mode, because I think a lot of the questions that we're going to have relate to that. I think that we have answered a number of questions during the presenters, and I want to thank again all that that Greg and Dries and John have contributed so far. So a couple that have come in. Here's another core, and I'm going to try to get to some of the questions that are core. So how do you use these techniques and the PF curve and your failure modes to predict the time before complete asset failure? Don't everybody answer at once.
Again, I think it's
Mm-hmm.
yeah, the concept there is you're not predicting failure. That's not what you're trying to do. You know, I can't predict failure. Much like if we liken practicing maintenance to medical practice or practicing medicine, have you ever gone to the doctor and it told you exactly when your heart's going to fail? Or exactly when your kidney's going to shut down? Or exactly when? No, they can't. That's not possible. It's not within our realm of comprehension. So therefore, why do we think that we can do that in maintenance? It's not going to happen. So what tools and techniques are your doctors and nurses using to help them diagnose the condition that you're in? And then they can then give you some kind of interval of when they believe you're going to enter into functional failure of your organs, which is critical. Okay, you can have a functional failure of your kidney, but you're not going to die. But if you don't address this functional failure soon rather than later, you will, perish. And
Right.
so we're nothing here can we predict the actual moment that you're going to reach total failure. But we have defined, when we go in and we actually do our FMEAs and our FMICAs or any other technique that you can apply, what we do find is, and we want to define, is the functional failure point. And that's what classic RCM, Nolan and Heap, that's what we talk about, especially with RCM2. All right, with Mowbray. What do we understand about functional failure? So if I have
10 seconds, Greg.
if I have a pump that's 120 gallons per minute, and that is the design state, and it's now pumping 119, it has functionally failed. But has the pump failed totally? No.
Okay, I'm going to ask one more core question, and I have a couple of things to get to. So the other core question that we have coming in, again, is the classic. Using these modes and the PF curve and the inspection techniques, how do you decide which inspection techniques to use for a given asset or component?
Well, once you've identified your failure mode, okay, now you need to apply the right tool or technique, all right, especially, when we're looking at the strategy that is most value add. In other words, you don't want to end up deploying technology to where you're chasing dimes with dollars. Doesn't make sense, not economically feasible. And so you need to find the right condition monitoring tool and technique that you can use so that you can position it to find the P on the
Right?
PF. That's what it's all about. So it may be time directed. It may be your regular PMs that you're doing, your inspection. It may not be a tool or technique that's found under condition-based maintenance. But then again, it may. Everybody's got to realize that when you create your job plan, when you're actually creating your task and procedures, each task and procedure is related back to a failure mode. And that task and procedure needs to be aligned with a certain tool or technique that you're going to be using.
Dries and John, how would you answer that question?
I think I would like to add to that last part is that's also experience based, right? That's maybe when it's time to pull in an external consultant, or you are not the only one with that piece of equipment, right? So there is experience and there is similar machines that have failed and success that has been reached already with certain techniques and a way of applying them. So I think that's also where it's time to reach out and say, hey, who can maybe help me here to bring some experience on board, right? And that's what I would like to add to that part of it.
And John, what would you add?
Actually, there's not much more to add because I think that Greg and Dries both did a great job of answering that. So again, I'm playing catch up and I don't have much to add. So no, great job, guys. Thanks.
Okay. I have a feeling that we could do another session on this, audience. You have been fantastic in asking your questions, and I want to assure you that we will write back with you. We will talk to Dries and John and Greg afterward and get you more thorough answers to your questions because you are fantastic. Thank you. I want to encourage everyone to come to the next session on October 14th. Tom Moriarty is a very well-regarded presenter on leadership questions around reliability. And as we all know, as reliability advocates, actually implementing a reliability program and getting it to stick within the plant is quite tricky. So Tom will be addressing some of the challenges around moving forward, advancing. If you are encountering a lack of progress with your reliability program, you might want to listen to Tom as he uncovers some of those challenges and how he advises moving forward. And then you may have the opportunity, if you attend Accelerate, to hear more from our three speakers today, Dries and John and Greg. Accelerate is an annual conference, and it has become increasingly popular over the years because of the sessions, just like today, actually, that go into quite a bit of consultative coaching on the whole curve and all the different tools and techniques used in reliability maintenance, everything from details on the CMMS into vibration and our other modes and modalities. So I encourage everyone to go to accelerate.excelix.com and have a look at this conference. Since it's virtual, it is easier to attend than ever. So one more reminder, when I close down the webinar today, a survey will pop up after the webinar closes, so stay on just a moment because we would love to get your feedback. If you do want us to do another webinar like today's session, let us know. Let us know what specific questions or topic areas you'd like us to address. And you will be able to see the replay of this webinar shortly up on the excelix.com website. And with that, I want to say a sincere thank you to all of our panelists today. This was fantastic.
Thank you very much.
Great, thank you.
All right, we'll see you back again soon. And thank you, everyone. Have a very good day.
Bye.